In our massively interconnected world, understanding geomagnetic storms is crucial to protecting our power grids, communication systems, satellite ops, and ultimately this modern society. It is that we are beholden to the moods of our star. Geomagnetic field perturbations are the footprints of its reach, with impacts that are far more serious than dazzling auroral displays. Forecasting the ground impacts of the space weather requires an understanding of coupled physics systems with cascading effects across spatial temporal scales. There's a need for AI or machine learning approaches that can remain relevant by improving over time or learn continuously. It is the Geoeffective continuous learning team here that will extend the capability of chained machine learning pipelines, so-called Dagger and Sheath, with rather non-trivial advancements needed to inject data streams from a variety of sources and deploy adaptive models that become reliable by evolving on the fly. They seek to provide predictions in real time, moving beyond single-use curated models to an ever-adapting, ever-learning system fit for the future.
Good morning, afternoon, or evening, wherever you are in the world. We are the Geoeffectiveness Continual Learning Team, and we are pleased to share with you our work. Our dream team spans multiple disciplines and domains and includes myself, India. I am our pipeline and web hosting production lead. Then we have Opal, who is our uncertainty quantification and interpolation lead. Next, we have Bubiti, who is our data and code deployment lead. Next, we have Chetrich, who is our machine learning and continual learning architect. And lastly, we have Mike as our faculty and cheerleader. With that said, what is our challenge? Well, the challenge is to see if we can reliably predict geomagnetic storms within a continual learning framework. In other words, we want to ensure that our models remain relevant and improve with the addition of future data sources in geomagnetic storms. But first, what are geomagnetic storms and why do we care? Well, we have solar events and features such as solar flares, coronal mass ejections, and coronal holes that occur on the surface of the sun. These events can produce everything from solar wind to high energy protons and solar energetic particles that travel through the interplanetary medium and come in contact with our geospace environment. This interaction gives us some of the pretty auroras that we see, such as the northern lights, but they can also cause severe damage to our technologically dependent society, harming our power grids, gas pipelines, communications, and space infrastructure, and even astronauts in spaceflight. Ground geomagnetic field perturbations are the direct drivers of the ground effects and an essential proxy for the rest. We need actionable and operational forecasting pipelines to predict these disturbances and mitigate their effects. But this is not the first time we have taken the route of machine learning to develop a predictive tool for ground effects. Previous FDL teams in 2020 and 2023 have already made progress in this direction. This problem was approached by breaking the sun and Earth's connection into two parts: one from the sun to L1, and second, L1 to Earth. As we have observatories at the L1 vantage point continuously monitoring the solar wind conditions, we can use these measurements to forecast the geomagnetic perturbations, which is exactly what the original Dagger was doing, ingesting a stream of L1 data and predicting the ground geomagnetic field. But Dagger only gives us a lead time of 30 minutes, so it does not solve our problem. We need a longer lead time. So during last year's challenge, the team went further and developed Sheath. Now, Sheath is a model that can predict the solar wind parameter at L1 using the data from the Solar Dynamic Observatory. It is prepared by the Analysis Ready data team in the same year's challenge. And with this, we can get a lead time of around 5 to 7 days when fed into Dagger. This year, we have taken yet another step forward, and I will now hand this over to Bubiti to tell us more.
Thank you so much, India. I am Vibhuti, and I will talk about further progress that we made while building upon the foundations led by previous teams. We developed an easily deployable forecasting pipeline, which offer a near real-time live inference with quantified uncertainties. On top of that, we aim to provide the model in a continual learning paradigm. One module suite that does all of these out of the box. We call it GeoCloak. Now, without any further delay, let's open this GeoCloak box and see its building blocks. The GeoCloak box has three key building blocks. The first is Seath, which predicts solar wind parameters at L1 using SDO data as input. The second building block, the newest version of Dagger, operate in two different modes. One that uses Seath prediction to predict low fidelity ground perturbation at supermax locations with 5 to 7 days of lead time. And the other uses near real-time solar wind data from ACE and Discover to do the same, but with higher confidence, but definitely at lesser lead time of around 30 minutes. Both these forecasts are then passed to the next block, where interpolation and uncertainty quantifications are performed, and the results are stored, later to be used for our live inference. Now let's go through these blocks individually to know how these blocks are working. And in this race, Seath is the first one to start with. So unlike previous efforts, we have used a multi-layer perceptron model at the heart of Seath. As mentioned, this model takes input from SDO data and forecasts solar wind condition at L1 with 5 to 7 days of lead time. We have developed two versions of this model. One that uses the extracted feature from SDO data, primarily the properties of coronal holes and active region across all wavelengths as input, and other that uses the SDO embeddings provided by our ARD team. In the plots, where we can compare the true and predicted value, we observe that the model are effectively learning the ambient solar wind condition. However, they are less accurate at capturing the peaks in these parameters, which is somewhat expected since we are not including any CME-related information in the model. Now, Dagger, the second block, can ingest Seath's prediction along with near real-time observation from ACE and Discover to further proceed in the pipeline. Chetraj will be explaining this in more detail. Chetraj, over to you.
Thank you, Vibhuti. Now I will be continuing our presentation by discussing the Dagger model within the context of continual learning, which is how to make sure our models remain relevant and are fit for the future. To quickly recap, as you can see in this figure, Dagger is an RNN-based model designed to time series data of solar wind parameters from ACE and Discover at L1. It then predicts geomagnetic perturbations at ground stations and uses an interpolation scheme to issue global forecasts. Continual learning for our project falls in the category of domain incremental learning. Our main objective with continual learning is to ensure that as the new data becomes available, the model can be retrained without losing its performance on previously used data. This is especially important since in a typical continual learning scenario, models often suffer from what is called catastrophic forgetting, where new information overrides what the model had learned previously. To tackle this, we introduced two strategies into our Dagger CL model. First, we employed a data resampling strategy. During each retraining stage, we randomly sample 40% of the instances from the dataset used to train the model in earlier stages, as shown in the figure. This allows the model to revisit some past experiences without overexposing it to the entire earlier data, which could lead to accumulated bias over time. Second, alongside resampling, we integrated a loss penalty approach known as EWC. It identifies important model weights after training on the initial dataset and preserves them during subsequent retraining stages. When new data is introduced, EWC applies a penalty to ensure these important weights don't change significantly. This enables the model to adapt to a new data while retraining crucial knowledge from earlier training, allowing it to perform well across both old and new datasets. Our evaluation shows promising results for Dagger in the CL paradigm, as seen in the plot, which tracks the model performance at each stage of continual learning using the same validation dataset. There's consistency in the performance and also improvements to a degree across our three evaluation metrics, MSE, which is also our loss function, root mean square error, and mean absolute error. The lower plot demonstrates that the performance remains stable with minimal fluctuations throughout the three stages of continual learning. Finally, here is an animation that shows the output of our Dagger model trained within the continual learning paradigm. It shows the predicted geomagnetic perturbations of the north component at ground stations. And with that, to further elaborate on the predicted outputs of Dagger, I will hand things over to Opal.
Thank you, Chetraj. So our aim is to make predictions of global geomagnetic field perturbations via sparse supermag magnetometer forecasts. There are less than 600 ground supermag stations, and they're spread around the globe, mainly located in the Northern Hemisphere. We approach this problem using a machine or statistical learning technique, namely Gaussian process regression. This technique assumes Gaussian noise and priors in a linear model. We can therefore predict the global mean and standard deviation of each geomagnetic field component via closed form expression. For the linear model, we use spherical elementary currents, which is a physics-based model that mimics the ionospheric current flows. And after rigorous comparison with other empirical and physics-based models, we found that the spherical elementary currents were the most accurate and certain. So overall, we were able to successfully predict geomagnetic field perturbations globally with quantified and reduced uncertainties. All this comes together in a GeoCloak web app, which is fully accessible to the community. This portal contains a dashboard with near real-time geo-effective data and predictions. This dashboard you are currently seeing is the real-time Dagger CL inference, which displays geomagnetic perturbations predictions around the globe for the east and north components, along with their standard deviations for quantifying their uncertainty. Our model is running on a remote virtual machine that is updating every 5 minutes based on our solar wind data from ACE or Discover and Dagger, with the outputs being pulled into the portal for visualization. GeoCloak provides an entirely new way to incorporate machine learning into operational space weather forecasting, and these efforts provide actionable forecasts for global ground geomagnetic perturbations for decision-making with quantified uncertainties. It also provides near real-time online inference in GeoCloak, which allows the community insight into our latest geospace conditions. And finally, GeoCloak is the first step towards geomagnetic continuing learning operational forecasts. This new paradigm ensures that the models remain relevant, improve, and are ultimately able to take advantage of new data, whether it's from new missions or solar maximum. And on that note, thank you everyone for listening.